Thanks for coming. And pardon my voice. I got a cold. I think Seattle is very hot, and there's this phenomenon called, hot sickness. I think I got that. I will talk about tracing, particularly its impact on latency analysis, and some of the upcoming features in Go 1.11. I'm working on our instrumentation stack at Google, and this is like partially what I'm doing for a living. So before starting, I will explain what tracing is and why it's useful. Pipes are very great to explain computer systems. I use them very often. And here you see a network of pipes. These are water pipes. And these are connecting subparts of the big system to transport water from one place to another. If you think about have you ever thought about the availability of such a system, or how can you actually measure or debug the availability? So there are various factors that may cause this system to have an outage. For example, is the pipe clogged, or is a pipe leaking and not pressurized enough? Both of these issues are affecting the throughput of the overall system. One other interesting aspect is also the path and the direction of the water, until it's served at the endpoint. We can easily diagnose what components are involved if there's an outage by answering this question. What would happen if water, as it's flowing, just leaving some hints behind? And we can generate the overall flow path by looking at these hints. Tracing basically allows us to do that and see things end to end until something is served at the end user to the end user. It can be water, it could be a function call, it could be an HTTP request. The basic principle is the same. We're tracing subcomponents to see what is happening end to end and to see the impact on the end user. So tracing is an umbrella term. I just want to, just expand it a little bit. It involves many ways of tracing things. Distributed tracing is one of them. In-process tracing is the other one. syscall traces is some people are familiar with that. Runtime traces, and there are other ways of doing tracing. Currently, what you're looking at is a distributed trace at the request RPC level, and the blue box at the top is actually what your end user is experiencing by doing an HTTP GET to /messages. But you, as the operator of this system, if you have distributed traces, you can actually see what else is going on. It turns out this is a distributed system. We are jumping from one service to another. We first trying to check the integrity of the request, and then we see if the user is authenticated. We do some cache lookup, and then the thing is not in the cache. That's why we query the database to retrieve the final results. And you can see how long it took for each subcomponent to respond, and most importantly, also you understand what subcomponents were required to serve this request. So this is another example. It takes 245 milliseconds in this case, but you see that it failed. The request has failed, and maybe the customer is on the phone trying to understand what is going on, because the endpoint is just returning an HTTP 500 something without any further messages, because user-facing error messages is usually the third hardest problem in computer science or something. So we can take a look at our distributed trace and see what happened, because we internally collect more data, more error messages. We usually don't map them to user-friendly stuff, but internally we know usually much better. So we can see what happened, fix the bug, and redeploy the service, and everything will be fine. This is sort of what happened when I joined Google. We had this layers of code, millions of lines of stuff. But one particular API call was failing, and I was able to pinpoint what happened and go back to my handler, fix the bug, and redeploy it. So I ended up deploying stuff to production on my first week, which was very easy. So I want to say this very strongly opinionating thing, I guess, but everything is in this constant state of becoming a black box without having any traces. I think people, even who are maintaining their own services, sometimes just cannot truly understand. The source code is not very scalable enough. to give you all the insights. I've seen lots of engineers rolling out distributed tracing for the first time, and they were shocked. Oh, there was supposed to be a fan out here, but I'm doing 10 sequential requests rather than 10 concurrent ones, and wasting my time. And it was not super clear, even though they own the source code, they can see it in the source code, but without seeing it visualized, it was not that clear. And also, the dependencies between different services, what triggers what, nobody has time to read and understand the big picture. So things are becoming black boxes without traces. Tracing often allows us to particularly debug two critical cases. The first one is the error cases. Where is the error is coming from? What is the root cause of the error? And the second thing is latency. Both are very critical to tell a system is available and there's not an outage, because from the user perspective, both latency and having no errors is very important. So latency issues are a little bit harder to pinpoint, unlike the error cases. So what causes latency? Who knows? Too many moving parts. We have network outages. We have scheduling issues. We have poor utilization. GC, computationally expensive code. It's hard to pinpoint. So writing servers is just quite fun, but maintaining and operating them is not that much. At any time, there are tons of requests going through a server. So they are interacting with the depending on this common primitives and components such as the runtime and affecting the overall of the state of the things. Some of these runtime events, for example, are scheduling, or we are doing memory allocation, or there's garbage collection going on. It's very hard to associate a request with its impact on the the runtime, and as well as the runtime's impact on the request under high load in a server. So if we go back to the pipe analogy, by using our distributed traces, for example, we usually can say that, hey, this pipe is the actual, we can narrow down the problem to say that this particular pipe is the problem, but it doesn't give us any further details what might be going on. And we cannot fix it if we don't know the root cause. So the pipe here might be clogged because a Go scheduler event, but we should understand the case and address it with an optimization if it's critical. And I'm actually glad that we don't have any pipes in the world. Requires Go runtime at this point. So, this is some sort of a common feedback we get our SRE. Hey, there is this there's no way for me to tell why latency is high. Can you just review our code and tell us if it could be GC or scheduler or syscalls, and who has that, right? Nobody is actually equipped to go through your source code and digest all these millions of lines and tell how to optimize. The solution here should be more about a diagnostics tool. So the execution tracer, the Go execution tracer, has been around for a long time. It's been contributed by Dimitri Kuo. It's the current de facto way to diagnose the Go runtime, but what it does is reporting fine-grained runtime events from a Go routine and reporting utilization of the CP cores. It cannot tell what specific user code is associated with the runtime events. And under high load, there's so much going on, and it's practically not possible to isolate a specific request and see its impact, so this tool becomes not that useful. So I will go back to my previous example, and I will focus on the second handler, the service, the authentication server, the access token handler for a second. So we have this 172 millisecond latency, and assume that this is not a very regular thing. There's an issue, but we want to figure out. We realize that there's no host or specific networking related issues impacting any of the machines. So we want to, see some maybe more from the process itself to what is going on. Execution tracer is adding this new feature that allows us to mark sections in the code, so you can simply, break down how much time is spent on where. So access token handler is executed and preempt executed in preamp. If you see those transparent boxes, it's kind of like representing that. And 1.11, with 1.11, execution tracer will be able to generate a report where the time is spent in those boxes. So we did some, networking. This is kind of like a final report. We did some networking for one little box, 6 to 8 microseconds, and then we executed also, which is 123 microseconds. We ended up like having some syscalls, 5 microseconds in this case, and then we had also some garbage collection happened in that little box. And you see that like the handler is consistent of multiple boxes, so we need to also sum up all these values to see the final report. The execution tracer is not just going to break down the data this way. It will also allow us to like visualize the overall flow. So the purple boxes here is the handler is when the handler is being executed. It's been momentarily blocked by I/O, waiting for an epoll, and then it executes, and then syscall happened, and it executes a little bit more. There's a GC, and then executes a little bit more. There's some I/O, and finally finishes. So this is some sort of data to watch for repeating patterns and addressing anomalies. So this sounds cool, but how we do it. The runtime trace package in the standard library is going to introduce new APIs to mark sections. So execution tracer, first of all, execution tracer is very expensive to keep it on all the time. That's why you want to enable it when you only want to diagnose what is going on. So you just want to record some data in production when there's an issue, there's a latency issue you cannot really address by other tools, and you just want to take a look at the runtime. And then you can typically use the regular execution tracer tool to visualize. There are 3 new concepts being added to this standard library package: regions, tasks, and annotations. They allow you to just mark codes and log, important events. So runtime can, associate these high-level concepts with its own events. So if a runtime event is, for example, triggered from your code, it automatically do the accounting, and it generates the report so you can see how much time is spent. It can be also used by distributed traces. It's possible to just go and dig into an RPC handler and what happened in the lifetime of an RPC handler, and that's very useful. So I said marking sections. That's why I want to give you a brief intro into the new APIs. We expect you to mark your code by marking the starting point and the ending points. We have 2 kinds of markers. The first one is region, the other one is task. This is how you, for example, mark a task. You just start, put your handler name there, and then end, and you write your code in between. Let me explain why we have 2 types. Because regions are the sections of the code that can not span among multiple Go routines. In order to do accounting, we need to start a region and end it at the same Go routine. We cannot span multiple stuff. And then we have this logical group called tasks. It's kind of like an easier way to query things. You just want to put everything under a logical group so you can easily search. For example, in this case, the task, if you start a task for an RPC handler, here the task 1 is starting at Go routine 1 and ending at 5. But regions, the execution of the handler is happening in multiple Go routines, and all of them, those execution parts are represented as regions by the green boxes. I don't know if you have ever used the execution tracer. It also is coming with a handler. So you import this package. It registers the trace handler on the default mux. And here I'm starting a server at 6060. And then, in production, what you can do is like curl that endpoint for 5 seconds. It's enabling the execution tracer and stops it in 5 minutes. You download the collected data and use the existing Go tool trace to start the web UI. The web UI, if you are not familiar, I would suggest you to take a look at the docs. There are better docs right now. So this is one of the new pages added to the new UI. In a demo program, what I did is actually like mark my gRPC handlers. This is an example from the gRPC hello world. There's only one handler, say hello. I have a middleware, creating a task in the beginning and ending it in the end, so it automatically like shows me this distribution, latency distribution. It collected 312 tasks because I made that amount of calls. And there are a few, 100 millisecond outliers in the distribution. If you click on the distribution bucket, it just takes you to this page where you can actually see more details. And here you see the important events and also like important annotations. And in this case, all of this stuff is actually have been overlapping with GC. The problem with the outlier, why they ended up being higher, is probably because of the GC. So I said that like each task is often made of multiple regions. We have another UI for the regions. You can see that like say hello RPC actually have like 5 regions. Again, you can see the distribution, and as soon as you click on things, this is where the things are becoming exciting because regions, as I said, supports accounting, so they can actually tell where the time is spent on. In this case, the con-ready regions, you can see that how much time is spent on execution, network, sync, block, syscalls, scheduler in GC. There are a few other UI changes that allows you to like see things and visualize the entire call chain, but I'm not going to talk too much about this in this talk. And want to go back to the initial point I made that you want to collect this type of data in production because latency violations are usually very hard to reproduce elsewhere. Since it's extremely expensive to keep this always on, do not do it. We only recommend it, momentarily doing it, gather some data, and turn it off again. You can register the existing trace handler and get the debug endpoint and just use it. And once you have the data, use the tool to visualize. These are the upcoming features in Go 1.11. So if you want to give it a try, please try because it's still beta. And it's very important, I think, just give things a try and like file bugs. After I gave this similar talk at a different place, several actually like bugs have been filed, so it's useful to have more opinions. If you want to have an example usage with distributed traces, I maintain this distributed tracing library. What it does is like each time you create a span, distributed tracing span, it also creates this execution tracer task. So everything you do is automatically being categorized under the distributed span. Once you see a distributed span is not acting well, you can just run the execution tracer and match the same name and like find the execution tracer task and anything underneath it. So this is again came from the gRPC hello world, and I didn't create it by using a middleware. I use a distributed tracing library. It automatically creates a span for every handler and every outgoing RPC call, and it automatically created the execution tracer tasks. So, nothing is perfect, and there are some problems with this new feature, at least some limitations, and I will explain. The first thing is the accounting. As I said, the regions need to start and end at the same Go routine, and it's terrible because we cannot do automatic. We need to do manual instrumentation everywhere in order to actually benefit from this. And there's some work planned to have adding some manual instrumentation for RPC frameworks such as gRPC. And NetHTTP package might be one of those as well. The other thing is the export format. I don't know if you have used the execution tracer, but its export format is like something not very easy to parse. And there's only one way to export it, and it's not very easy to automatically attach these additional bits into your existing distributed traces, for example. So you need to like switch back and forth between your distributed traces and your execution tracer UI to kind of understand what is going on. I wish that there was one source, one visualization tool that can display all of this stuff. Before wrapping up, I want to give you two, recipes. The first one is like for web and RPC servers. We really recommend you to have like distributed traces in place, and then you automatically create tasks for those traces, trace spans, and in latency violations, find the service and the particular handler if you can. The problem is caused at and rule out all the network and platform-related outages, and then record execution tracer data for a limited time and take a look at the data and see. And the second one is more focused on batch processing. For example, if you have a book processing job that reads from multiple that reads source from multiple books and processes as it's reading, you can mark workers, those processors, with the book name. Then you can see like what book is impacting the process in which way. So even though the limitations I've just mentioned, that I think this is filling a gap to further diagnose things, and it's a good addition for everyone who is maintaining Go in production, especially with the accounting available. Now we have the visibility into the runtime and how we affecting it, and as well as how runtime is impacting our code. So questions and comments are welcome. Bugs are also welcome. My email works. I'm Rekil everywhere else. So thank you much.